Okay, in this video we're going to go through examples 3 and 4. So here we have the double replacement reaction of barium nitrate and sodium phosphate to produce barium phosphate and sodium nitrate. So we have a 112.2 milliliter sample of 0.28 molar sodium phosphate, and we're adding it to 150.6 milliliters of barium nitrate that has a concentration of 0.15 molar. So this is a multi-part problem. The first question is, what is the net ionic equation for this reaction? So remember, in a net ionic, we remove any spectator ions. So spectators ions start and end aqueous. All right, and typically anything that is group 1 or a nitrate will be a spectator as long as it started aqueous. So group 1, sodium's gone, it's aqueous and aqueous. And if this one's a spectator, the thing that it's attached to must be a spectator as well, might be a spectator as well. In this case, it is nitrate, so we don't care about it. So then we bring everything down. Now remember, net ionic, you have to have your charge. No charges, it's not a net ionic. So we've got 3 bariums. Barium's from group 2, so it's got a +2 charge. Now, phosphate is a polyatomic ion with a -3 charge. If you forgot that, you can work backwards. We've got 3 sodiums, which comes from group 1, so it has a +1 charge. So PO4 3 minus, and this makes 1 barium phosphate. Solid. Okay, so the question is, how many grams of the precipitate will form? So again, we have information about our 2 reactants. So it's going to be a limiting reactant problem. So we'll convert it to moles of our precipitate. Now, we start with milliliters, so we need to convert those to liters to begin with. And we do that by dividing by 1,000, or to save space, 10 to the third. Next, to go to moles, remember molarity is moles per liter, so we're just going to multiply. Now we know we only care about the phosphate from the net ionic, but this is the formula that it comes from. And then we have our ratio of 1 barium phosphate for every 2 sodium phosphates. Our milliliters are gone, our liters are gone, and our sodium phosphate is gone. So let's just do this out. 112.2 over 1,000 times 0.28 and then divided by 2. We get 0.015, actually 16, 2 sig figs from here, moles of our precipitate. And now we check the barium nitrate, doing the same kinds of steps. So convert our milliliters to liters, then multiply by our concentration. To get into moles. And then use our mole ratio. So if we double check, there's 1 barium phosphate for every 3 barium nitrates. Alright, so let's see what we get there. 150.6, 10.15, over 3. Oops, and I forgot to divide that by 1,000. That would have been embarrassing. 0.0075 moles of the barium phosphate. So which one of those is limiting? Well, this produces fewer moles, so this is our limiting reactant. Now again, remember, when I'm referring to limiting reactant, it's actually this compound here that's the limiting reactant, but that's how much we're going to make. So we'll convert that into grams. Now we do need the molar mass of this compound, and it's going to be a bit big. That's a massive substance. All right, so if we double check a periodic table and add that up, we're going to have 2 bariums. This is where we're going to use parentheses. So 1 barium is 137.33, but we've got 2 of them. And then we have 3 bariums. And then we have 2 phosphates. So 1 phosphorus is 30.97 plus 4 times 16. Close our parentheses. And we get a molar mass of 601.93 grams. Multiply that by our prior answer to get our our grams, and we end up with 4.53 grams of barium phosphate should be made. And I'm just writing in theory, because I saw the next question's asking us 4% yield. All right, so we're told how much we actually produce. We're told that we make 3.74 grams. We have our theoretical, so the ratio of those will give us our percent yield. 4.53 grams times 100. So our grams cancel. All right, and this should be over 50%, probably close to about 70-ish, 70-80 range. And we get 3 sig figs, so that will be 82.6%. All right, now let's look at example 4. A 5.37 gram piece of magnesium is added to excess hydrobromic acid to produce hydrogen gas according to this balanced equation. The it's great that the acid is in excess, but we're producing a gas, and we can see this part here is going to be about some gas stoichiometry using the ideal gas law. So the first part is how many moles of hydrogen gas are produced. So we need to convert the grams of magnesium into moles of hydrogen gas. So we're just going grams to moles, so that is a two-step problem. Divide by the molar mass of what we're starting with. So check that, that's 24.30. And then we multiply by the mole ratio of hydrogen gas, one of those, to every one magnesium. So magnesium's gone, that's gone, great. So 5.37, help if I was typing on the calculator. Divided by 24.30, and we get 0.221 moles of hydrogen. Pretty straightforward there. And now B. If the gas was collected at 28 degrees Celsius, we have a temperature at a pressure of 0.931 atmospheres, we have a P. We want to know what the volume is that this gas will occupy. So it's going to be an ideal gas law problem. PV equals nRT. So let's rearrange that for V to begin with. So V equals nRT over P. Remember, N is moles. So we got that in the previous part. So our volume will be equal to 0.221 times our gas law constant. So we check our formula sheet. Where is it? Here we go. So we have to find the R value for the pressure unit we have. Joules is energy. Here we go. Atmosphere. So 0.08206. 0.08206, and that's got a bunch of derived units in it. It's liters, atmospheres per mole per Kelvin. I could have written this liters, atmospheres over mole over Kelvin, but I wanted to write it the way you'll see it on the exam. And my temperature is in Celsius. We have to convert that to Kelvin by adding 273. 28 plus 273 gets us 301. And then we divide all of this by our pressure of 0.931 atmospheres. Before continuing on, let's double check that everything's going to cancel. Mole and per mole are gone. Atmospheres up there and down here. Per Kelvin and Kelvin. Great. Leaving us with just liters. Parentheses are our friend with a question like this. So we're going to take our moles, multiply it by 0.08206, and multiply it by 301. So that will give us 5.46 liters over 0.931, and we'll get a final volume of 5.86